So yeah, hi everyone, and welcome to this NITheCS Mini-school series, so entitled Introduction to Quantum Thermodynamics, an Open Systems Perspective. So just to perhaps give my own personal introduction. So for those of you who don't know me, I'm currently a postdoctoral researcher at Stellenbosch University, and so I'm based in the Quantum Sun research group, which is headed by Professor Francesco Preciazioni, so whom some of you might know as the current interim director of NITheCS. And so, yes, I'd also like to just thank NITheCS for giving me the opportunity to present this mini school. And so, yeah, just to say, the kind of the philosophy behind these kind of lectures is to kind of just give you a kind of basic flavor and understanding of some of the kind of foundational concepts of quantum thermodynamics, and then hopefully you can use this to go on and develop your own understanding or use it in your own research, perhaps. Okay. Okay, so here's the structure of the lectures will be outlined as follows. So as I'm sure you're aware, there'll be 4 lectures, so starting with the day, obviously, and then we'll be on a weekly basis. And so, so this first lecture is kind of just to give a kind of gentle introduction to the field and to kind of motivate why we're interested in studying quantum thermodynamics. And then to also just kind of go over and review kind of foundational concepts. And so, yeah, also I should say that I'm kind of approaching this mini school from the perspective that maybe some of you in the audience don't have a particular background in quantum theory and quantum statistical mechanics. So I've tried to make these lectures as self-contained as possible. And so, yeah, today I will be reviewing kind of foundational concepts and also in particular the theory of open quantum systems, which I will kind of use routinely in the second, third, and fourth lectures, and also just briefly reviewing equilibrium descriptions. And so lecture 2 will kind of go more into, so yeah, today is more kind of review. Next week's lecture is kind of more going into the actual quantum thermodynamics, how we can analyze these systems in terms of Markovian master equations and also developing the first and second laws. And then the third lecture will be more on kind of applications, so to how we can apply this kind of Markovian description to describing heat engines and refrigerators, and also looking at particular examples. And then the fourth lecture is kind of more going to slightly more advanced material, so looking at how we can generalize this type of the previous framework that we analyze into treating strongly interacting open systems. Okay, so yeah, to start, I'll kind of motivate why we're interested in studying quantum thermodynamics. So just to start, as I'm sure some of you are already aware, so macroscopic thermodynamics are the type of thermodynamics that you learn in undergraduate physics and was developed mainly in the 19th century. So this is kind of a classical phenomenological theory, which is interested in describing kind of the average behavior of heat, work, and entropy. So what I'm mean by average is that macroscopic thermodynamics isn't interested in describing the behavior of individual particles or their properties. It's more looking at how we can come up with ensemble level descriptions, so a collective behavior, or a collective description of the behavior of something like a gas, and how we can describe this, how we can characterize its behavior in terms of things like heat, work, and entropy. So what quantum thermodynamics is interested in doing is taking these kind of established classical ideas and of, say, for example, heat and work, and extending them into the microscopic domain. So trying to apply them to, or develop equivalent laws which apply to systems whose behavior is fundamentally quantum and has to be described using using quantum mechanics. And so to kind of illustrate or to motivate this a little bit more, so in this slide, I've put a picture of a steam engine. So I'm sure many of you are kind of familiar with the concept of a steam engine. And so this picture here is actually of the so-called the Flying Scotsman steam locomotive. So I think it was the first steam locomotive that breached the 100 miles per hour barrier. And so this type of this train is a kind of canonical example of a heat engine in macro that we can describe using kind of standard classical macroscopic thermodynamics. And the kind of on the right hand side, what I've done is kind of put a kind of schematic that's kind of meant to illustrate thermodynamically, like in basic terms, how this operates. So the idea here is that we have some we have a hot reservoir and we have a cold reservoir, and we have some kind of system in the middle here, which I've denoted by C. So this is kind of a classical system, and so this is sometimes also described as the working medium of the engine. And so the way this kind of this engine in this locomotive works is that you have a hot reservoir which supplies energy in the form of heat to the working medium. So in this case, like the hot reservoir is essentially the furnace that is fed with coal at the back at this part of the train. This then heats water to produce steam, and then this goes to the working medium here is essentially a gas in a piston. And then what this does is it basically then the supply of heat then causes this gas to expand, which basically drives the piston, which in turn drives the wheels of the train, which is effectively what makes the train move. And so essentially in this schematic, what happens is that the heat is supplied, and then a portion of this heat is converted into work, so mechanical work, which is the energy that's used to drive the train. And then in the latter stage of the cycle, what happens is that our working medium, so as it expands, it cools, and then in the latter stages, it then is compressed again, which causes the steam to compress back into water, and then during this stage, some extra heat is dissipated into a cold reservoir, and then the cycle continues. And so this is essentially kind of like a kind of very common example of a kind of classical heat engine. And so what we're interested in doing in quantum thermodynamics is kind of taking the extreme limit of this kind of situation. So rather than having a working medium which is described, whose behavior is described using kind of classical thermodynamic laws, having a working medium in which rather than being, for example, made up of a collection of particles which are of the order of Avogadro's number, we can take the extreme limit and say, okay, what if our working medium is just a single particle or like a single atom whose behavior is intrinsically quantum? And so in this situation, we can no longer rely on microscopic thermodynamics. We have to kind of develop a new theory. And essentially that's what, at least in part, one of the main applications of this area is, can we come up with a thermodynamically consistent description of such systems in terms of things like heat and work? Okay, so as I just mentioned, one main area of thermodynamics, quantum thermodynamics, is in the description of thermal machines, so heat engines and refrigerators. And so what I'm trying to convey here as well is that quantum thermodynamics is kind of quite an extensive field in its own right. So it doesn't just encompass things like thermal machines, it encompasses other things, like, for example, it's interested in more kind of foundational questions of quantum mechanics. So in particular, things like thermalization. So to date, it's still kind of an open question of how isolated quantum systems thermalize. So if you take a system a quantum system and you leave it long enough, eventually an isolated system long enough, it will eventually evolve into a thermal state or eventually equilibrate. And so there's still kind of open questions around, well, firstly, how for what system, understanding why certain systems do thermalize and why certain systems don't, and also kind of understanding more in depth what the mechanisms behind thermalization. And so this kind of sub area of quantum thermodynamics is also deeply connected to kind of ideas in quantum information. And so there's also the kind of quite topical and quite recent area of thermodynamics, which comes under so-called stochastic thermodynamics. And so in stochastic thermodynamics, what we're interested in doing is looking at kind of small scale systems, so those below the thermodynamic limit. And so in these types of systems, because they're small, their quantities like heat and work fluctuate. And so the interest in this kind of stochastic thermodynamics has kind of been driven with the kind of recent discovery of these so-called fluctuation theorems. So I won't go over this in detail, but fluctuation theorems are essentially these theorems that characterize the out of equilibrium behavior of small scale systems in terms of or in relation to the equilibrium behavior of microscopic systems. And And so this can be analyzed in a classical setting, but there's also kind of a lot of interest recently in developing kind of stochastic thermodynamics from a quantum perspective. And so in this mini school, these are kind of more kind of advanced areas of the field. So I won't really, this is to kind of just give you a flavor of some of the applications of the field. So I won't, for the remainder of these lectures, I won't really go into either thermalization or stochastic thermodynamics. Although in the third lecture, I'll go part into some, in focusing on applications to things like heat engines and refrigerators. So yeah, as I said, the kind of the purpose of this mini school isn't to give you like a really in-depth, comprehensive review of the field, which you know, practically speaking, in 4 lectures it's almost impossible to do. It's kind of just to equip you with the basic knowledge such that it can help you develop deeper knowledge or interest in the field, you know, through going on to look at other sources. So in particular, I've listed some kind of useful literature here. So that's also helped me in writing some of these lectures. So so the first example I use is this book which came out in 2018. And so I think this is likely to date one of the most kind of comprehensive reviews of the field. So I think it has something like over 100 contributors, and it kind of analyzes it from both or provides a review from both a kind of theory perspective and also experimental perspective. So there's also this book from, I think, 2019, which was written by Sebastian Defner and Steve Campbell. So this is an introduction to quantum thermodynamics, so from a theory perspective, but also connecting it more, looking at it from the perspective also of its connection to quantum information. And so there's also these 2 review papers, or sorry, this first review paper by Saibin Janathathy and Janet Anders. So this is, I think, is one of the earliest reviews into quantum thermodynamics. And also this archive paper by Paul Potts, which is an introduction that kind of more focuses on applications to thermal machines. Okay, so I should say that the field in itself, so quantum thermodynamics is a still relatively young field, and so a lot of the work is still primarily theoretical, although there has been, at least in the last 10 years, some kind of seminal experimental results that I wanted to highlight. So here I've just I have included some figures which kind of illustrate two notable examples. So one, which is a work that was done in 2016 in the group of, I think, Ferdinand Schmidt-Keller at the University of Mainz in Germany. And so what they did here was they implemented an experimental version or a microscopic version of a so-called Otto cycle. So an Otto cycle is a kind of thermodynamic cycle which you can implement, it can be analyzed in terms of macroscopic thermodynamics. And so what they did here was kind of take this idea and scale it down to essentially the level of a single ion. And so the kind of platform that they used to implement this kind of Otto cycle is an ion trap. So which is kind of illustrated in this figure here. So on the left-hand side here, you have a kind of linear pull trap. So this is a trap which is made up of these 4 electrodes. So these are these kind of red rods in the figure, and these each of these electrodes produces an RF field, which in turn traps, in this case, a single calcium ion in the center. So in this diagram, this is represented by this kind of green dot. I'm not sure if you can see that. And then these blue lines are both a probe and a cooling laser. And so the idea here is that you can then, in this kind of setup, you can implement a thermodynamic cycle in the following way. So on the right hand side here is kind of a schematic illustration of this cycle. So it's kind of broken down into kind of 4 processes. So you have a kind of cooling phase and a heating phase, and then a work injection and a work extraction process. So on this left-hand side, you have this kind of, so I should say that these axes, so the left or the y-axis is the mean photon number. So this is kind of like a measure of the temperature of the ion. and on the bottom it's the trap frequency. And so what they do is they basically, in this stage, you have a kind of heating phase where heat is supplied to the ion to raise its temperature, and this is done through effectively injecting white noise into the trapping field. And then you have a so-called kind of expansion phase where basically work is extracted from the ion. And then you have this kind of cooling phase, which is basically the reverse of the heating phase. So the cooling laser is basically used to reduce the temperature of the ion. And then you have a last kind of compression phase where the trap frequency is basically increased. And so overall, this is kind of like a thermodynamic cycle, which is kind of in a certain way analogous to the kind of classical engines, which also operate under an Otto cycle. And so this was interesting because it was kind of, as far as I'm aware, one of the first experimental demonstrations of a microscopic engine. So I should emphasize that this is not a quantum heat engine per se, because it largely still operates in the classical regime. So in particular, the state of this ion it remains in a thermal state throughout the cycle. So its behavior isn't intrinsically quantum. So on the other hand, so there's a kind of more recent experiment which was performed, I think, at the University of Oxford in the group of Klatso et al., which was published in 2019. So this was a kind of, to my knowledge, like the first experimental demonstration of a quantum heat engine that shows some kind of quantum advantage over its classical counterpart. And so by that, I mean, by quantum advantage, I mean that you can exploit the quantum properties of the system to extract, in this case, a higher output than you could achieve classically. And so this was performed using nitro-vacancy sensors. And so I think this also implemented a quantum Otto cycle, but it implemented this cycle in the so-called small action limit. And there was, I think, at least a paper published before this work was done, which basically showed theoretically that you could implement an Otto cycle, a quantum Otto cycle that could outperform an equivalent classical Otto cycle. So that's essentially, this work was an experimental demonstration of that theoretical prediction. And so this if you're interested in learning more about this, there was also a paper published or a physical viewpoint that was published in 2019 that kind of explains this experiment in more detail, and also some of its some future implications. Okay, so hopefully that introduction has kind of motivated why we're interested in studying quantum thermodynamics, and also hopefully conveying some of the basic ideas of the field. So in the remainder of this lecture, I'm just going to essentially review kind of foundational quantum mechanics. So in advance, for those of you who already have quite a extensive background in quantum statistical mechanics and thermodynamics, I perhaps apologize. I just wanted to make sure that in this first lecture, for those of you who maybe don't have as much of a background, that at least in principle, we're more or less all on the same footing before I start looking at more advanced material in the later lectures. So yeah, so I will review kind of the theory of isolated quantum systems in terms of time evolution, things like the spectral theorem, and introducing the idea of the density matrix. And then I'll go into the more kind of important material, which is to do with the theory of open quantum systems. So introducing the reducement density matrix and the idea of quantum maps in terms of describing the time evolution of an open system. So this material here is the material that I'll be using or relying on in also later lectures. So I'd say it's kind of the most important part. And then I'll at the very end, I'll just briefly touch on equilibrium descriptions, and then to provide a brief summary. Okay, just before, I can see there's like a question in the Q&A. Maybe I can answer it before we start with the lecture. I have just a general question. How can classical thermodynamics evolve from so I'm not sure if I understand your question. So I think, are you asking more how quantum thermodynamics can kind of advance our understanding of classical thermodynamics? That's, I guess, what you're asking. So I think I'm not sure exactly how to answer that question, but I could say, let me just go back, sorry. So I could also say that, well, intrinsically, I would say that the systems that we're interested in analyzing are fundamentally quantum, right? So perhaps the way that I could answer your question is by saying, or at least partly answer your question maybe, is by saying, if we're looking at kind of more foundational questions of thermodynamics, so things like, for example, thermalization, or things like fluctuation theorems, if we analyze this from a quantum perspective, then this will also potentially give us some kind of, it can potentially inform us as well on the classical behavior of these types of systems, or the systems in the classical setting. I'm not sure if that answers your question. Okay. If not, then please type any follow-up questions. Okay, so I've overviewed the content of the lecture. So okay, let's start. So here I'm just going to go over like a very I'm just essentially going to review the kind of the main concepts of foundational quantum mechanics. So as I'm sure some of you are already aware, so the state of any quantum system, an isolated quantum system, can be basically represented by a vector which lives in a finite dimensional vector space, which here I denote by H. And essentially this vector space is can be viewed as effectively a set of all possible physical states. And in a kind of each of these states can be represented, in the finite dimensional case, each of these states can be represented as in a column vector form. So in terms of these, in these coefficients, which are referred to as the probability amplitudes. So these coefficients are can be used to basically determine the probability of obtaining a particular measurement outcome when we measure our system. And an important aspect of this is that this vector space is defined over a complex field. So each of these coefficients can be complex. And so since this, so here just to also say that I'll use the words Hilbert space and finite dimensional complex vector field interchangeably. So since this Hilbert space is an inner product space, it can be associated with a scalar product. And so the scalar product of any two states is defined in this way. And this relies on the definition of a so-called joint of this vector. So in kind of in Dirac notation, this vector is referred to as a ket, and the corresponding adjoint of the vector is referred to as the bra. So the inner product is obtained as the multiplication of the bra and the ket. And so this adjoint lives on the corresponding adjoint space to H. Okay, and so a kind of key property of quantum states is that since these states characterize the statistical properties of our system, they have to be normalized. So I mentioned that these coefficients are going to determine probabilities, and we know that probabilities have to be normalized to 1. And so a kind of physical kind of constraint imposed on each of these states is that they have norm 1. So the norm here is just defined as the inner product of any state psi with itself. And so because the norm of any state is invariant if we take a state and multiply it by some arbitrary phase factor, this doesn't change the norm. And so these states are effectively defined up until like a global phase factor. And so another way of saying this is that quantum states are equivalence classes of unit vectors in our Hilbert space. And so our vector space can be, if we assume it to be separable, we can assume it we can associate it also with an orthonormal basis. So this is just a finite collection of orthonormal states. So these are just states whose inner product is basically given by the Dirac delta, the Kronecker delta. And the implication of this is that any state in our Hilbert space can basically be written as a linear combination of these basis vectors. And also just to point out that these coefficients depend on which basis we express our state in terms of. Okay, so the way that we describe time evolution in quantum mechanics is through the so-called Schrodinger equation. And so time evolution is governed by a unitary operator. So here, which I denote by U. So this U is essentially it's a linear map on our Hilbert space. So it basically takes as input some quantum state, and it maps it to another quantum state at some later time. So here, this parameter T is like a time parameter. And so we assume that we can initialize our system in a particular state, and then this unitary operator maps it to a state at a later time. And so yes, so this kind of unitary time evolution is equivalently captured in terms of the Schrodinger equation. So essentially, the Schrodinger equation is a differential form of this unitary time evolution. And this operator H here. So this operator in a finite dimensional case can be expressed as a matrix, and this is this operator contains essentially it's self-adjoint, and so its complex transpose is equal to itself, and it basically contains the dynamical details of the time evolution of our system, depending on what system we're describing. And so this is common. This operator is commonly referred to as the Hamiltonian of the system, and so. The reason why time evolution is described in terms of a unitary operator is because it essentially conserves probability. So if we compute the norm of a state after it's been evolved under this unitary operator, then it's equivalent to its norm at times t equal to 0. And what we can show, I'll now go into this on the next slide, is that what we can do is we can use the so-called spectral theorem, which to tell us that this unitary time evolution operator can be written in the following way. So it can be essentially written as the exponential of our Hamiltonian, including these extra constants and t. So also I should just say here is that this constant h bar, this is so-called the reduced Planck's constant. So it's Planck's constant divided by 2 pi. So yeah, so this is a constant, whereas t is actually a time argument, so it's a variable that changes. Okay, so essentially the spectral theorem is like a kind of crucial theorem that's used kind of extensively in quantum mechanics. So what this theorem tells us is that any normal operator acting on a Hilbert space. So a normal operator is one which satisfies this property, is diagonal with respect to some orthonormal basis. So in other words, any normal operator can be basically diagonalized. And in this representation, this is also called the spectral decomposition of this normal operator. And these states here, so the states that make up this orthonormal basis, they are eigenvectors of our operator A. So that basically just implies this relation, and these A's are the corresponding eigenvalues of our operator A. And so here we assume that we're working in a finite dimensional space, so we assume that this sigma here just denotes the finite set of eigenvalues of our normal operator. So some kind of important classes of normal operators are self-adjoint operators, which I mentioned in the previous slide. So the Hamiltonian is an example of a self-adjoint operator. And so also observables. So observables relate to measurable quantities. And so these are represented in terms of self-adjoint operators. And the reason why they're represented in terms of self-adjoint operators is because it can be quite easily proven that the eigenvalues of this operator are always real for a self-adjoint operator. And so these eigenvalues, in fact, represent the different possible measurement outcomes that we can obtain when we measure a particular observable of our system. And so an example of this kind of relates to the Hamiltonian. So the Hamiltonian is a self-adjoint operator that is the kind of the energy of, it represents the energy observable of our system. And so essentially the eigenvalues of this operator basically tell us the different possible energy levels that our system can be in. So as here represented by these EKs. Yeah, so the reason it's called a Hamiltonian is because I think this language is basically adopted from kind of classical Hamiltonian mechanics, where the Hamiltonian is a quantity that is given as the sum of the kinetic and potential energies of a conservative system. Okay, so another kind of implication of this spectral theorem is that if we have some kind of analytic function, which is a complex function, then the function of any self-adjoint, or the function of any normal operator A can be just written in this way. So basically what this tells us is that the function f acting on A can just be obtained by basically applying A to each of the f to each of the eigenvalues A of our normal operator. And so this implies that since so another example of a normal operator is a unitary operator. And so this implies that that the time evolution operator that I introduced on the previous slide can always be written in the following way in terms of the eigenvalues of our Hamiltonian. And you can then, so basically you can use this to prove the equivalence between the Schrödinger equation and the time evolution described in terms of this unitary operator U. Okay, so measurements are also another important part of quantum mechanics. So here I only talk about projective measurements. So basically, for any observable, so for any self-adjoint operator A that has this spectral representation, we can, the probability of if we measure our system, then the probability of obtaining a particular measurement outcome A is can be computed in the following way. So yeah, in other words, if we basically, since these A's form an orthonormal basis, we can expand our state psi in terms of these basis vectors. And then you can show that this basically relates to like the norm squared of these probability amplitudes that I mentioned earlier. And so we can also characterize like the statistical properties of our system. So if we want to look at like, if we perform many measurements of a particular observable, we can look at it, the average measurement outcome. So that's what's characterized in terms of this expectation value. And so the way that we generally compute that is in the kind of normal classical way. So we basically just sum over each of these measurement outcomes weighted by the corresponding probability. And from this definition, we can rewrite this in this way. And we can equivalently write this in terms of this so-called trace operation. So the trace operation, so for those of you who don't know, is like a trace operation is basically, so if we take this object that's written inside this trace, so inside these brackets, this can be represented as a matrix. And so if we represent this matrix in a particular basis, then the trace of this is just basically the sum of its diagonal elements. And just an important point to emphasize is that the trace is independent of the basis in which it's performed. Okay, so the reason why it's kind of useful to write the expectation value of an observable in this form is because it then introduces the idea of a density matrix. So a density. So far we've been characterizing quantum states in terms of. So we characterize our system in terms of just a state which we label as the ket vector psi. But you can actually develop more kind of general types of states which can't be represented in just terms of a single ket vector. And so another way of saying this is that we can, if we consider another type, if we consider like an ensemble of kets, so rather than just have a single ket, we can have an ensemble where we have multiple different possible states, which each are associated with a certain probability. And so the reason why these represent a kind of more general class of states is because they enable us to describe quantum systems that there is some kind of uncertainty in the preparation of the system. So, for example, you could have, I don't know, like an atom or something, and you can prepare in a state. But if there's some kind of, say, for example, we just have like a black box, and we press a button, and it prepares our atom in a particular state. We can have a more general scenario where we basically press a button, and then with a certain probability, it will prepare our atom in one state or a different state. The overall state of our atom can't just be described in terms of a single ket because there's this extra additional uncertainty. And so the way that we have to do that is by introducing the idea of what are called mixed states, which can be characterized in terms of this like density matrix. And so the way that we can compute the expectation value of an observable in terms of a system which is described by this ensemble is in the following way. And so this can be, just using the same logic here, this can be written in terms of the trace of our operator multiplied by this quantity. And this quantity we can define as rho, which is the density matrix. And so, so just also to clarify, so if we just to compare this expression here to this one up here, this is any density matrix that only contains a single ensemble member. So where we don't have this sum over, each of these members multiplied by the probability, these are referred to as pure states. So these these are the states which can be represented in terms of just a single psi ket. And so mixed states are ones which are of this form, which we can't just represent as a single ket. And so the important properties of, and so also, yeah, just to say that the reason that it's also called a density matrix is because it's kind of the analog of a kind of classical probability distribution for quantum systems. So, this trace can be effectively viewed as the analog of, when we compute the expectation value of a random variable in classical probability, we integrate we integrate over the different values with respect to a probability density. So in this sense, this operator kind of fulfills the role of a probability density, but for quantum systems. And so some kind of intrinsic properties of the density matrix are the fact that it has unit trace. So this is kind of a consequence of the fact that our probabilities have to be normalized. So the probabilities have to sum to 1. So this follows from that. And so this is the density matrix is also a Hermitian operator. So that can just be straightforwardly demonstrated from its definition. And it's also positive. So it's positive in the sense that if we take any vector that lives on our Hilbert space, then this quantity is always non-negative. So an equivalent way of also phrasing it is that it's because this is the density matrix is a Hermitian operator. This is saying that the eigenvalues of the density matrix always have to be non-negative. Okay. So we can also talk about we can also come up with a slight generalization of the Schrödinger equation. So the Schrödinger equation describes the dynamics of a quantum system which is characterized by a pure state. So we can extend this to quantum systems whose states are mixed using the density matrix. So we can so for such systems which are characterized by mixed states, the equivalent equation that describes its time evolution is the so-called Liouville-von Neumann equation, or just the von Neumann equation. And its time evolution, so this is essentially just analogous to the time evolution I gave on the previous slides, but also applying to mixed states. And so here I've also included the possibility that the Hamiltonian of our system is time dependent. Okay, and so the way that you can kind of derive this is it just follows directly from essentially the definition of the density matrix, and also from the Schrödinger equation. So so this relationship here just comes from so the time evolution of each of the kets, so psi, j, and our ensemble, is individually described by the Schrödinger equation. So its time evolution is obtained by just applying this unitary operator. And so essentially, if you just plug in the definition of the density matrix into here, you can see that this is just equivalent to the unitary time evolution that I gave on previously for pure states. And so you just start with this definition of time evolution, and then you can then just take the time derivative to then quite easily show that this just gets you to this equation here. So this object here is referred to as the commutator. So it's basically just equal to so the commutator is of, say, for example, h and rho is just equal to h multiplied by rho minus rho multiplied by h. And so, yeah, this is just a shorthand notation for what's on the second line. Okay, so what this does, so the Liouville von Neumann equation describes the dynamics of a system which is either pure or mixed, that is either in a pure or mixed state. And so the reason why density matrices are crucial for formulating a kind of theory of quantum thermodynamics is because the kind of the pragmatic model that we consider in well, not just quantum thermodynamics, but thermodynamics in general, is that we have some kind of system that we denote by S, which is placed in contact with some kind of thermal reservoir, which here I denote by R. And so, so in general, this what we call here this reservoir, it's a macroscopic system, so it's a system that we assume to be much larger than our quantum system, and it's one in which we assume that we essentially have no control over. And so it essentially just is meant to model anything that could it surrounds and is able to exchange energy or particles with our quantum system. And so we assume that our reservoir, the general assumptions is that we assume that our reservoir is in thermal equilibrium. So it's can be internally, so it's internally in thermal equilibrium, so it can be associated with some temperature T. And so so what we now will look at doing is kind of formulating the basic ideas of open quantum systems theory. So this is looking at how can we describe the properties and the time-dependent behavior of some kind of quantum system that is in contact with a thermal reservoir and generally exchanges particles and energy with it. Okay, so the starting point is to kind of rely on our previous theory. So what I did in the previous slide was go over how we can describe the properties of isolated quantum systems. Obviously, in this setup, our quantum system here is not isolated. But what we can do is to kind of derive to kind of analyze its behavior. We can start by assuming that our system and reservoir are isolated, so we can describe them at a global level. And so to do this, we can introduce we have to describe this as a composite quantum system, and the way that we do that is by noting the fact that the Hilbert space of our composite quantum system plus reservoir is given as essentially the tensor product of the underlying state spaces of our open system S and our reservoir R alone. And so what this basically means is that if we want to write down a pure state of our system and reservoir, then we can do it in the following way here. So basically our global Hilbert space is written as the linear combination of all possible of the tensor product of the states which form orthonormal bases of just our system S and our reservoir R alone. And so from this definition of an arbitrary state, a pure state of our global system, we can also write down the corresponding density matrix. So this just follows from the definitions that I gave on the previous slide. Okay, and so now we can kind of use this. So this describes, so this sign, this row here, describe the possible pure states and mixed states of our system plus reservoir. And so, as I said, we're generally interested in looking at just the behavior of our quantum system without necessarily looking at the properties of the reservoir. And so the way that we can kind of formally do this is by introducing the idea of what's called a reduced density matrix. And to kind of get to this, what we can do is we can look at computing the expectation value of a local observable that just belongs to our open system S. And the way that we can construct such observable is by just taking the tensor product of some observable, which here I denote by AS, and then tensoring it with the identity the identity matrix for the reservoir. And then just using the definition of the expectation value in terms of the density matrix that I gave previously, we can write this in this way. We can write the expectation value in this way. And what we can show is that this is equivalent to, what we can do is we can break up this trace into a trace that's just performed with respect to a basis of our system S, and then also with respect to a basis of our system R. And what we can show is that, yeah, so we can introduce the reduced density matrix as essentially a quantity which is obtained by taking the partial trace of the density matrix of our global system. So by partial trace, so the partial trace is defined in this way, and the way that we implement a partial trace is by basically performing the sum, where these mu's here are basically states which belong to an orthogonal basis of our reservoir. And so you can see here that this reduced density matrix is an object of the open system alone. So in a way, what we're kind of doing with this partial trace operation is we're kind of taking our global system and then throwing away information about the reservoir, and then coming up with a state that only characterizes the properties of our open system alone. And so this density matrix is called the reduced density matrix. So yeah. Okay, and so and you can kind of, so I've kind of only kind of gone over the basics of this, but you can kind of more formally show that the reduced density matrix contains or it completely characterizes the statistics of our open system. So in the sense that if we are interested in just measuring an observable property of our open system without caring about the reservoir, the reduced density matrix contains all this information. So it contains effectively the same amount of information as the state of psi did for an isolated system. So from this point of view, we can now formulate, if we're interested in looking at the time evolution of our open system. So as I said, our open system S generally interacts with this reservoir, and due to this interaction, its state will change with time. And so the way that we can then describe this is in this way. So we just start from, so what this equation here expresses effectively just the definition of time evolution that I gave for the density matrix. And then what we do is as I said, we perform this partial trace operation to recover just the density matrix of our open system, the reduced density matrix of our open system. And so one way that we can kind of simplify this expression is by assuming this so-called kind of separability criteria. So this density matrix rho here is the state that belongs to our open system plus reservoir. And so to kind of simplify things, what we can do is say, okay, we can assume that the initial state, so at time t equals 0, can be represented as the tensor product of just the reduced system density matrix, and at times t equal to 0, and also the corresponding reservoir state. And so the reason why this kind of maybe just appears a bit unintuitive, but essentially the reason why we can make this assumption is because it massively simplifies the description of time evolution of open systems. But what this kind of implies is that our system and reservoir are initially uncorrelated. So the reservoir initially contains no information about the properties of our system. And so if we make this kind of assumption, what we can do is rewrite this equation in the following way. And then we can just use the definition of the partial trace that I gave on the previous slide. So just to emphasize here that these mu states represent these are basis states belonging to the state space of our reservoir. And then we can kind of rearrange this expression in this kind of more suggestive form. And then what we can do is we can write this in terms of these so-called Krauss operators. And so what this expression basically does is it tells us how to, if we have a system which is open in the sense that it's open and interacts with a reservoir, we can describe its time evolution by taking its initial state at times t equal to 0 and then evolving it according to this prescription in terms of these what I call Krauss operators. And so essentially in this kind of panel at the bottom, this is essentially what I say is that the time evolution of an open system under this separability condition can be described in terms of a quantum map in this particular Krauss form. So so here, so what I mean here by quantum map is some kind of object that takes our the state of our system at t equals 0, and then maps it to a state at some later time t. So in a way, it kind of it's a kind of generalization of this unitary time operator that I mentioned on the previous slide. So when we wanted to evolve an isolated quantum system in time, we use this unitary time evolution operator. To do so equivalently with an open system, we can, under this separability criteria, we can use this kind of quantum map. And formally, this basically is defined as a linear map that takes that basically maps physical states of our open system onto other states. And so this map here, this map is represented in the so-called Krauss representation. And so I won't go into too many details here just due to time, but in the next lecture, I'll use this kind of idea of a quantum map more extensively and how it also relates to how we can describe dynamics in terms of these so-called Markovian master equations. So here, I'm only really just briefly introducing the concept of a quantum map. I'll go over it in a bit more detail in the next lecture. But formally, so so this map is expressed in terms of these Krauss operators, and these Krauss operators satisfy this kind of closure condition. So they aren't unitary, but the sum of like the adjoint and the Krauss operators sum to 1. So in the case of, so when I talked about this type of time evolution under a quantum map being a kind of generalization of unitary time evolution, we can kind of see that if we just take the special case where we only have a single Krauss operator. So when alpha is equal to 1, then we can see that from this condition, we just have k is equal to the identity, which is basically just the unitary condition that we had previously. So in the special case where we only have one Krauss operator, we recover just unitary time evolution. So yeah, hopefully that kind of better conveys the concept of this type of time evolution in terms of a quantum map as being a generalization of unitary time evolution. Okay, so but yeah, just to emphasize, I'll kind of talk about this more in the next lecture. Okay, so I think we're coming towards the end of the lecture. So just to kind of wrap things up, I wanted to kind of just introduce some kind of quantities that are important in characterizing like the quantum systems that are kind of in equilibrium. So an important quantity is the so-called von Neumann entropy of a state. So the way that we can define the von Neumann entropy of a density matrix is in the following way, where this constant Kb here is the so-called Boltzmann constant, and so just using this definition, we can show from the fact that because the density matrix is a self-adjoint operator, it emits a spectral decomposition. And we can show that this form can be equivalently represented in this way, where these lambda a's are the eigenvalues of our density matrix. And because the density matrix is positive, these eigenvalues are non-negative. So you can see that this is a well-defined property. This object is well-defined, and it's also non-negative. And so kind of conceptually, what the von Neumann entropy does is it kind of characterizes the uncertainty we have about the preparation of our state in terms of its density matrix. So so one way of kind of showing this is that in the extreme case where we have a pure state, so if you recall, a pure state is one in which our system can be just described in terms of a single ket. So this corresponds, in terms of the spectral decomposition, this corresponds to the case where we only have one term in this sum and the corresponding eigenvalue is 1. And so you can see in this case that the von Neumann entropy of this pure state, if we just plug this into this definition, then the von Neumann entropy is 0. So that basically conveys the fact that we have almost perfect information about the preparation of our state. Whereas in the kind of more general case, when we're dealing with mixed states, where we have a sum over kind of other non-zero eigenvalues, then there's the von Neumann entropy is non-zero and is positive. So this kind of conveys a lack of information about preparation, or kind of, you can think of more equivalently the von Neumann entropy as representing the amount of information, the average amount of information that we gain about the state of our quantum system when we perform some kind of, if we measure some particular observable. Okay, so So the von Neumann entropy is kind of important in characterizing like the equilibrium properties of our system. So one way we can think about this is in terms of like maximization of entropy. So what we can do is we can, in general, show using another object, which is called the relative entropy. So the relative entropy is just defined in this way. And so I won't explain what this is so much, but I would say an important quantity of the important property of the relative entropy is that it's non-negative. And what we can then do to show is we can just use this inequality to show that the von Neumann entropy of some arbitrary state rho is always upper bounded by this object here, which we can show is always less than or equal to this so-called Gibbs entropy. And so this introduces the idea of what's called a Gibbs state. And so basically a Gibbs state is a state that basically characterizes, or it's a state that basically maximizes the von Neumann entropy of a system, which is in equilibrium at some fixed temperature. So here in this expression here, beta is the inverse temperature. So this is 1 over the Boltzmann constant times by temperature. And this Z is the so-called partition function. And the Gibbs, so for those of you who have maybe some knowledge of classical statistical mechanics, so the Gibbs state is essentially equivalent to the canonical ensemble. So the canonical ensemble is a thermodynamic ensemble that describes the statistical properties of a system which is in equilibrium, a system which is in contact with a thermal bath. Okay, so I think maybe now is a good place to stop since we only have a few minutes left. So, okay, so in this lecture, I kind of introduced kind of quantum thermodynamics as an extension of the macroscopic thermodynamics to the microscopic domain, so involving systems whose behavior is non-trivially described by quantum mechanics. So we've kind of reviewed some kind of foundational concepts of quantum probability and statistics. So we also looked importantly at the time, I introduced the idea of open quantum systems and formulated the time evolution of an open system in terms of a so-called quantum map. So this is something that I will talk about more in next week's lecture, and I'll also kind of elaborate more on the idea of a quantum map in next week's lecture. And then we also just went over some kind of introduced some kind of other quantities that are useful in characterizing equilibrium states. So yeah, in next week's lecture, as I said, I'll kind of go over Markovian master equations, which are also ways of describing the dynamics of open systems in contact with a thermal reservoir. And then we can use this to then introduce the notion of the first and second laws of thermodynamics. Okay, and so with that, then I'll end by just saying thank you for your attention. And for those of you who are interested, so I belong to the Quantum at Sun group here at Stellenbosch University. And so if you're interested in looking at what other kind of research our group does, then feel free to visit this our website at quantum.sun.ac.za. Okay, thank you.
Thank you so much, Graeme. So there are 3 questions in the Q&A. And there was a request that, can you please read the question out loud before answering it, because they are not visible to the attendees.
Okay, shall I just go through because I can see the Q&A. Should I just go through the Q&A?
Yes, but please, yeah, please read the question first before answering it, because
okay.
Yes.
Okay. So yeah, so the first question is from I'll probably mispronounce your name. So from Cobus Labush Shang. Sorry if I mispronounce your name. So so his question, or their question says, is the quantum map similar to the idea of trajectories, some function that describes the motion of a particle at t = 0 and then at some later time t? So yes, so the quantum map is conceptually related to the idea of quantum trajectories. So what I would say is that the quantum map describes time evolution at the level of the full ensemble. So, but what quantum trajectories does is it describes the dynamics at the level of individual ensemble members. So in other words, if you look at like individual trajectories and then you average over all these trajectories, how our system evolves in time, then it gives you the equivalent description that you would get with a quantum map. And so I'll talk about this. Well, this is kind of, I'm not sure, when you say trajectories, I'm not sure if you mean in terms of quantum trajectories that you can obtain when you perform like an unraveling of a master equation. I'm assuming this is what you mean by trajectories. So this is something, so yeah, in next week's lecture, I'll introduce the Markovian master equations, and these trajectories are kind of more intimately connected to these master equations than they are necessarily to the quantum map. So what I mean by that is that you can kind of formulate the idea of quantum trajectories by doing performing like an unraveling of the so you do this at the level of the master equation rather than at the level of the map. So okay, hopefully that answers your question. Okay, so we have a second question from Adrienne that says, a question about your notation. What does the double-lined 1 represent? Which slide? Sorry, I'm not sure which slide this is referring to. Sorry, let me go. If it's possible to write into the chat which slide it's referring to. Okay, so yeah, sorry. I'll skip over this question for now, but if you could just write in the the chat which slide this is referring. Okay, perhaps the state normalization. Let me go back. Oh, do you mean in terms of the? If you mean in terms of this, where is it? I'm assuming when you say double-lined 1, you mean this thing here. So this I kind of like 1 thing. So this represents the identity matrix. So this is here. This is just the identity matrix of the corresponding to the state space of our reservoir. I'm not sure if that answers your question, or if you're referring to something else. Okay, so let me look at the other questions. So are you going to use the Lindbladian? Yeah, so next week when I discuss Markovian master equations, a particular focus of that will be on these so-called Lindblad master equations, or Guarini-Kosakowski-Schudersan Lindblad master equations. So I will go over that next week. So sorry, that question was from Vineth. And so final question from Karabo Lesholo. It says, the section on quantum maps and Krauss operators was quite vague, and you move relatively fast. Do you mind glossing over it again or giving useful resources, because the rest of the, okay. Sure, yeah. So, so just due to time, maybe I can point you towards other sources. But as I said during the lecture, I only just very briefly introduced the idea of a quantum map here. So I will go in the beginning of next week's lecture, I'll go into more detail about this. I will describe more in detail the idea of a quantum map, or how we can formulate the properties of a quantum map, and also connect it to other things like master equations. So yeah, I apologize if it was a bit brief today, but I can maybe point you to some other sources. So in particular, at the bottom of this slide here, there's these lecture notes on open quantum systems by Daniel Lidar. So you can access it through this archive link here. There's also the book that I recommend. So this is the book of Heinz-Peter Breuer and Francesco Petruccioni, which is on the theory of open quantum systems. Yeah, so hopefully that also answers your question. And so, yeah, so just another question is, what is the analog of microstates in quantum dynamics? Is it the psi? So yeah, yeah, if I go back to the last slides, this one. So yeah, so I said that this Gibbs state is equivalent to the canonical ensemble, and so in that aspect, the corresponding microstates are represented as individual states in this ensemble. So this Gibbs state is clearly a mixed state, right? So it can be written as the sum over individual pure states multiplied by a corresponding probability. So this probability is just the probability that's taken from the canonical ensemble. So it's just e to the minus ek over kbt, where ek is the corresponding the energy of the microstate. And then these the corresponding pure states are the the state associated with each are the microstates essentially. If that answers your question. Okay. I think that answer. I don't think there's any. Okay, maybe there's. Okay, I don't see any more questions.
Okay, thank you so much, Dr. Graeme, and thank you to the participants. See you all next week, same time, same place, and more open quantum systems. Thank you.
Sure. Okay. Thank you so much. Thanks again, everyone.